Very much for the invitation. And I'd like to talk about a project which was going on with Nick Early and Leonid Monin. And I thought that because it's about Alcoved polytope, and that's the Alcoved polytope Alcoved conference, that should be a very fitting topic. By the way, I won't see the chat, so if you have any questions, just unmute yourself, or if anybody else could let me know. But yeah. The plan for the talk is that I want to start with an introduction to Alcoved polytopes. And then the main question I'd like to study is the type fin of Alcoved polytopes, and the last third I'm going to specialize to Alcoved simplices. So Alcoved polytopes, they were introduced by Lamb-Posnikoff about 20 years ago, and it's a class of polytopes having just a very special set of inequalities. Namely, they're given by the condition that the sum of the coordinates is 0, and then they're given by the condition xi minus xj less or equal aij for some parameters aij real numbers. And this just particularly means that the normal vectors to the facets are just in root direction ei minus ej. So essentially this means that we have a class of polytopes where the main condition is that all facet normals are in the parallel to the roots ei minus ej. And for convenience, I'd like to work in this hyperplane where the sum of the coordinates is 0, and I want to denote this hyperplane by hn. So there are a few examples. The one example which will appear later on again is the class of Alcoved simplices. So whenever we have a permutation, let's say sigma is a permutation on the element on the set 1 to n, then this gives rise to a Alcoved simplex delta sigma in my hyperplane hn, where I just look at the permutation of the coordinates, and then I demand that x of the first coordinate, so sigma 1, is greater or equal to x of sigma 2, and so on and so forth, up to x sigma n, and then I wrap it up again, this should be greater or equal to x sigma 1 minus 1. So this defines a simplex, and for every permutation we get such a simplex. Another class of Alcoved polytopes are order polytopes. So these are whenever we have a finite post set on the elements on the set 1 to n minus 1, with this order relation, we can define a polytope where xi is less or equal to xj if and only if I is less than j in this post set. And I add these xi minus xn so that this entire polytope is bounded. Another interesting class are matroid polytopes, and Posnikoff observed and proved that matroid polytopes are Alcoved if and only if the underlying matroid is a positroid. So this means that the matroid has a realization of the real numbers where every minor of this matrix is non-negative. This is not Alcoved on the nose in my coordinates. There one has to do a small coordinate change, but after this coordinate change, the polytope we get is Alcoved if and only if the matroid is a positroid. So that's a sort of interesting class of matroids, which is connected to Alcoved polytopes. There are two, from my point of view, there are two more motivations to look at Alcoved polytopes. If these aij's, these parameters are integers, there's a sort of canonical triangulation of these polytopes, which is called the unimodular Alcoved triangulation, which we just cut the Alcoved polytope by translates of the hyperplanes xi minus xj. So we look at all hyperplanes xi minus xj equal to L. For L some numbers, we cut this polytope, and then this cuts it up into these Alcoved simplices we discussed before. So sort of a schematic picture is we look, if you have this triangle, then we could just cut it with all these translates of the sides, and then we cut it up into all of these little simplices from this picture. And so for these class of polytopes, there's a sort of natural triangulation we can consider. Another connection is that to tropical geometry, because Michael Josvik and Kalekulas observed that these Alcoved polytopes are also, they call them polytropes because they are also tropical polytopes that are also convex in the usual sense. So there's in tropical geometry, there's a sort of tropical way of adding and multiplying. This gives rise to, you can talk about the tropical convex hull of a set. This is then what people call a tropical polytope, And if this happens to be convex in the usual sense, then this is a very special class of polytopes. That's what they call polytropes. So these are also exactly the Alcoved polytopes I care about. The closely related concept is that of generalized pentaedra. So these are polytopes where all edges are parallel to these roots, to ei minus ej. Here, so as I said before, for Alcoved polytopes, my facet normals are parallel to the roots ei minus j, and for a generalized pentaedra, the edges are parallel to ei minus j. This implies that these generalized pentaedra are closed under Minkowski sums, but they're not closed under sections. And so for Alcoved polytopes, it's the opposite. So Alcoved polytopes are closed under taking intersections, but they're not closed under taking Minkowski sums. And the main question I'd like to study here, say we have two Alcoved polytopes P and Q. When is there some P plus Q again Alcoved? So as I said, so this will not be true for all Alcoved polytopes. I'll show an example where this does not happen, but I'm interested in the question, so when does this actually happen? Two motivations. So one way, if we understand when we can take them I have some understanding of when we can take the Minkowski sums of Alcoved polytopes, we could hope to build up new Alcoved polytopes by sort of these atomic pieces of Alcoved polytopes and just combining them, and we get larger and larger Alcoved polytopes, which might be interesting.
Lucas, sorry, we have a question in the chat.
Yes.
Andon is asking, what does it mean to add two Alcoved polytopes?
So I mean that I want to take the Minkowski sum of these two polytopes. So whenever we have subsets of R to the n, we can look at their Minkowski sums by looking at all points which arise as sums of points of these two summands. So P plus Q means I look at all points in R to the n which can be written as P plus Q, where P is in capital P and Q is in capital Q. So that's the Minkowski sum. And the second motivation I would like to mention is that this is closely related to the type fan of Alcoved polytopes. And that's what I'd like to define and explain explain this connection in more detail. So that's what brings me to the second part. I'd like to discuss the type fan of Alcoved polytopes. So let's say I write P of Aij, which is the Alcoved polytope with these parameters Aij I chose. Then the first thing I'd like to look at is the so-called support cone, which I call Cn of Alcoved polytopes. That's a cone in R to the n times n minus 1. So these parameters, there are n times n minus 1 many parameters. So I can view them as a vector in R to the n times n minus 1. And now would like to look at the subspace in this thing. So it's a cone where all hyperplanes xi minus xj equal to aij actually touch the polytope P aij. This means would like to look at at those parameters such that all of these defining inequalities are actually touching the polytope. They don't have to be facet defining, but they should at least these hyperplanes of these conditions, they should at least touch the polytope. And that's what I like to call the support cone. And so these are sort of the minimal choices for these AIJ. So if they wouldn't touch, you could decrease the value of these AIJ without changing the polytope. And proposition, which was proved by Lam-Postnikov, also by Jostvik, and which is maybe sort of well known in this community, is that this support cone has a very concrete and nice description. Namely, it's the what is also called the metric cone, where these are the set of parameters Aij, where they satisfy the triangle inequality. Namely, you want that Aij plus Ajk should be greater or equal to Aik. This is the usual triangle inequality, and the result says that those parameters which satisfy the triangle inequality are exactly those parameters which minimally define Alcoved polytopes, which are so in the support cone. And these are linear inequalities, so it defines a cone in R to the n times n minus 1.
Question.
Yes.
For that final equation there, does that mean it is the set of alpha ij for which there exists a k which satisfies the triangle inequality, or is it all the ij for which for every k it satisfies the triangle inequality?
I think it means that for all choices I, j, k, different indices, they have to satisfy this inequality. Or maybe I don't understand the question.
Well, the set is a subset of the aij.
Ah,
So for any given I and j, do you only require that there exist one k which satisfies the triangle inequality, or all of the k?
no, I think I want to demand that if you fix ij, I think I want to demand that for all other k's, for all other k indices k, this inequality holds.
Okay, great, thanks.
Thank you. Now we have a cone, and this cone is sort of the space of all Alcoved polytopes, because that within that cone we all our parameters for Alcoved polytopes live. And that cone I want to subdivide it to a fan, and in the following manner. So the type fan, which I call Fn, is the causes subdivision of my cone Cn, such that for all t is a cone in that fan, if I pick these parameters aij and aij prime in the interior of this cone T, then the normal fans of the associated Alcoved polytopes agree. So NF is the normal fan of this polytope, and so I subdivide my cone by different shapes of the normal fan of these Alcoved polytopes. So the meaning is that the rays of the normal fan are fixed. These rays are all just some of the roots, because that's by definition of Alcoved polytope. But we don't know how these rays are assembled to the normal cones of the normal fan. And I just want to record the different ways of assembling these rays into the normal cones in the type fan. So meaning that the one cone, or at least the interior of one cone in this type fan, is the place where all these rays are assembled to the normal cones in precisely the same way. And the reason I'm interested in for this question is the following proposition, which says that if I have two Alcoved polytopes P and Q defined by my parameters Aij and Bij, then the sum P plus Q is Alcoved if and only if I view them as elements in my cone or my fan, then these Aij and Bij are in some common cone of my fan. So this means that the type fan knows all about when these Alcoved polytopes add, because they add if and only if I have 2 points in my cone which are part of some larger cone of my type fan. So this means understanding, yeah.
As you know, ask, so if I have two vectors in the same cone, then I get the same normal fan. But do I have a unique normal fan for every facet in this subdivision? Do you see what I'm saying?
So can you say again, please?
I guess like I could have a cone over here where if I take 2 in here, I have the same normal fan. Can I have another cone over here where that gives me like the same normal fan up to some isomorphism or something like that? Or is it just like...
I'm not sure. I think it could happen that you have 2 different sort of facets, so maximal dimensional cones in this type fan, where these normal fans are, well, isomorphic. Certainly, there could be some permutation acting on these cones, but I could also imagine that they would still have the same normal fan, but I'm not sure.
Okay, thanks.
Either way, I'm saying that understanding when to Alcoved polytopes, the sum of the Alcoved polytopes is again Alcoved, is equivalent to understanding the structure of the type fan of Alcoved polytopes. And the first result I'd like to report on in this project is the following. It says that if we let's say we have k Alcoved polytopes P1 to Pk in Hn, and assume that they are pairwise compatible, meaning that Pi plus Pj is Alcoved for all indices I and j, then their total sum, so P1 plus all the way up to Pk, is again Alcoved. So this means that if we say now we have k Alcoved polytopes, which we'd like to think about whether we can add them, it's equivalent to knowing whether we can take each pair of them and add them, and then we can also add the entire sum. And this in particular implies that if we going back to the question of understanding the type fan of Alcoved polytopes, this means that the combinatorial structure of this fan is just determined by its two-dimensional cones. Because suppose we knew all the rays of that type fan, which we don't, but let's assume we have sort of the finite set of rays of all this type fan. Now I look at all pairs of these rays, and I can check whether these pairs of rays form a cone in this fan or not. And once I collected all these pairs of rays which are compatible, I can just imagine I draw a huge graph where the rays are the vertices. I connect them by an edge if and only if these two rays form a cone, and then all cones of this normal fan are just the clique graph, are just the cliques of this graph. And by that meaning, and that's what I mean by that, the structure of f of this fan is determined by its two-dimensional cones. All right, and so I just said, suppose we knew all rays of this type fan, which is of course impossible, or at least we don't know all rays yet, but we do know some set of rays. Namely, we know that simplices are rays, and so I'd like to study the case of Alcoved simplices because they are all rays in the type fan. And I'd like to generalize the notion we have as a bit by sort of also being able to talk about lower dimensional Alcoved simplices, and the combinatorial gadget I'd like to use with that are ordered set partition. So an ordered set partition is just a partition B1 up to BL where I care about the order of the blocks of the partition. So I say an ordered set partition is this tuple B1 to BL where I care about this order, and B1 up to BL is a partition in the usual sense of the set N. And whenever I have such a partition, no ordered set partition, this gives rise to a simplex, Alcoved simplex delta S, defined in the following way. I demand that xi is equal to xj for all indices ij which are inside one block. So then xi is greater or equal to xj for all neighbors appearing in bk and bk plus 1. And then I wrap around again in the beginning by saying that xi is larger or equal to xj minus 1. And lastly, I would like to denote by sigma s the normal fan of the Alcoved simplex delta S. First, I'd like to try to understand sigma s, because if we understand sigma s, and so because we'd like to understand when can we add to Alcoved simplices, we can add them if and only if the common refinement of the normal fans is again a normal fan of Alcoved polytopes, so meaning all rays of this common refinement are in root direction. So we just, first of all, I'd like to understand, have a combinatorial description of the normal fan sigma s. And for that, I define a graph GS, where on the set N, where I have which is partially directed, meaning it has undirected and directed edges. I'd like to have an undirected clique for all BI. So for all the elements appearing within one block, I have an undirected clique, and I have a directed edge from BI to BI plus 1, where these are the smallest elements of the blocks. So let's look at it. An example, if I suppose I have the ordered set partition 1, 2, 3, 4, so 2, 3 is one block, then the inequality description is just as written here, where I just have x2 is equal to x3 because this is one block. And then the graph looks like this. So I have x2 is one clique, here's just one edge, and then the others are connecting the smallest elements, and the directed edges are connecting the smallest elements of each block. And then the observation is that this graph already describes the normal fan, because the linearity space is just the span of these undirected edges, and the generators of the rays and the quotient sigma s modulo the linearity space are just the directed edges in this graph. So if we want to understand or look at the normal fans, all we have to look at is these graphs. This also already tells us that sigma s is invariant under cyclic shifts of our partition, because the graph doesn't care about if we cyclically shift our order Z partition. And another proposition observation we made is that these order Z partition is a combinatorial gadget, and they actually capture all Alcoved simplices. So every Alcoved simplex in this hyperplane is equal to some delta S up to shifting and dilating the simplex. Okay, now let's come back to the question: when our two Alcoved simplices and the sum, when are they compatible? So I can add when can I add these simplices? For that, I take the union of these two graphs. So I have a graph GS, I have a graph GT. I take the union, but for T, I take GT op, meaning that I reverse all directed edges. And now we have a sort of simple combinatorial criterion when the common refinement of the normal fans is again an Alcoved normal fan, or when the sum is Alcoved. And this has to do with a cycle in this graph GST. We call a cycle violating if two conditions hold, if it has at least two disjoint segments in GS, and if it visits every vertex at most once. And the result is that the polytopes are Alcoved if and only if we can't find such a cycle in our graph GST. So we sort of, by looking at the cycles of this graph, we can decide whether the sum of these two simplices is again Alcoved. And we can look at an example here. Let's look at the example S is the partition 1, 2, 3, 4. So here's just singletons, and T is 3, 2, 1, 4. So the orange graph is the graph of GS. So I go from 1 to 2, 2 to 3, 3, 4, and then loop back 4 to 1. The purple one is the graph of T, but I reverse all edges, so they end up being the same. I also go from 1, 2, so I kind of read it backwards. I go from 4, 4, 3, 4, 1, 1, 2, 2, 3, 3, 4. And I want to recall, sort of look at the GS as upper edges, and these purple I drew below. And now we can easily find such a path which sort of loops changes between upper and lower edges, which is such a cycle, which I call violating, and this shows that the sum of these two Alcoved simplices is not Alcoved. So that's the smallest example where this happens, and that's, as I said, an example where we have two just simplices and their sum is not Alcoved. So that's one of the situations we need to avoid. For this motivates the following definition. We say that two of these order Z partitions are 4 interlaced if exactly happens what we saw in the last example, namely we find, so there should be a C, if we find indices A, B, C, D, which are distinct, and if I restrict my first partition to A, B, C, D, they look like A, B, C, D. So they look like 1, 2, 3, 4 we saw in the previous example. But if I restrict my second partition to A, B, C, D, then they are exactly these twists we see this twist we saw before, namely we see C, B, A, D. And if this happens, we call it 4 interlaced, because we see by looking at the cycle before, there was sort of an interlacing between the upper and the lower graph. There are 2 more of these patterns we found on 6 elements, so it's sort of the same now, but now for 6. Again, we demand that restricting S to these 6 elements is just the standard order, but restricting T to these 6 elements gives us again such a funny interlacing these 2 particular patterns, because also for these patterns we find a similar graph which interlaces between the upper and lower edges in the graph on the 6 vertices. But sort of surprisingly, and we found that this is all we have to worry about. So if we have an ordered Z partition on n elements consisting of singleton blocks, so as every block is just one element, then we found that S and T is the delta S plus delta T is Alcoved if and only if S and T are not 4 or 6 interlaced. So that's sort of a local finite condition, because the entire thing is Alcoved if and only if we just have to look at subsets of size 4 and 6, and we need to make sure that on these subsets of size 4 and 6, we don't find this interlacing pattern we just discussed. And in general, this is also true for general ordered set partitions, but then we just have to say, well, it's Alcoved if and only if for all subsets of size n of size at most 6, the sort of restricted simplices, the sum of these restricted simplices is Alcoved. That's sort of a local picture, which in some sense remotely echoes the well-known fact that if we have a regular subdivision of hypersimplex, which we would like to check whether it's a matroid subdivision, we just have to check if every octahedron is subdivided in the right way. So it's also a sort of local way of checking whether a matroid subdivision or a subdivision of hypersimplex is matroidal. And here, in some sense, in spirit, I don't see a connection, but in spirit, it's similar to say that checking whether the sum of these simplices is Alcoved, we can reduce it to a sort of local check on 4 or 6 elements. So this brings me to the last slide. So with like open problems. So we talked about, suppose we knew all rays for the type fan. This is of course a big assumption. We know the ray, we know that the simplices are rays, but we don't know many other rays. We know I know two more classes of examples. So I know that order polytopes are rays and connected positroids. So I told you positroids are Alcoved polytopes. They are not all rays, but the connected ones are rays. So rays are sort of those polytopes which you cannot write as Minkowski sums of smaller polytopes. So they're sort of Minkowski indecomposable, and order polytopes and connected positroids are of that type. And then even for these two families, we don't know yet which order polytopes or which connected positroids are compatible, meaning that if I have two connected positroids, can I take them in Minkowski sum? I don't know. That's also an open question. Thank you very much for your attention.
Right. Thank you so much, Lukas. Do we have any question for Lukas? You can either write them in the chat and I read them for you, or you can just open your mic.
I had a question, but it's mainly just about sort of intuition-based things. So a lot of these arguments kind of feel very similar to they feel somehow connected to the procedure that gives you like the sort closed interpretation of the Alcoved triangulation, like from a Grosvenor basis perspective. Do you know what I'm talking about?
Yes, so I mean, that's the original paper by Lamposnikov where they compare these different triangulations, and it turns out that they're all the same in the end.
Yeah, and it's like you take these pairs of sets and then you do this sorting procedure, and you get out a quadratic square-free Grosvenor basis, which is giving you the Alcoved triangulation, but it boils down to pairs of sets. You only needed to boil it down to pairs of simplices. And then even the interlacing procedures that you had, like 4 and 6 interlacing, it even has this vibe of sort closure. So I was curious if somehow in the details of proving these things, like that sort of sort closed structure of the triangulation is somehow playing a role. I don't know. It's a very question.
That's it. No, so no, the answer to your last question is I don't think so. At least we don't talk about any of these sort closed. I looked at it in the beginning, but I haven't looked at it for some time, and maybe it's worth going back to that. Thank you for your comment on that, but I don't see an immediate connection.
Yeah, it might be that, like, because at the end of the day, you're taking your Minkowski sum and checking if it still has this nice triangulation, which would have this interpretation. So it might be some sort of other explanation for the sort of interlacing properties that you're using. Yeah. But it's very, very beautiful stuff. Thanks.
Thank you.
Mm-hmm.
We also have a question from the chat. Sam is asking, you can define Alcoved polytope for any type, right? Any chance for something similar in types B, D, etc.?
I'm not sure. Yes, Sam is of course right. I mean, here, this is the sort of type A part of the story where I demanded the facet normals are roots of type A, but you can also look at polytopes where the facet normals are roots of type B or D. I don't know. I haven't thought about that, and I don't think that the arguments or the techniques directly translate to type B, but maybe with some more effort. But we haven't looked into that yet.
And then I guess last question, Lujun is asking, is there any relation between when Alcoved polytopes add and when generalized permutohedral intersect?
Ah, nice question. I'm not sure. I think that there is some duality which between maybe even on the level of L convex and M convexity, which might be worthwhile to sort of connect, which might connect these two sides stronger and then gives results in the direction of this question. But I don't know yet.